uh, uh, consider the experiment, and each outcome of the experiment we assign a real number. So basically it is a real valued function with a domain as a sample space. And I gave you the example that how the numbers are assigned to each outcome, and this number depends upon how do you define the function. So function you can define in terms of the words also, or in terms of the mathematical formulation. So here I gave you another example where you can define your function in form of mathematical function a plus b plus c, and then accordingly for each outcome the values can be calculated. They can be put in the tabular form, and at a later stage, if you are interested, you can calculate the probabilities also. So it probability x equal to 3, x equal to 6, you can calculate. Now, when we deal with one particular random variable, then the range we denote it by Rx. Usually we denote it by Rx, but when we are dealing with one random variable, we can drop this subscript. We can just write the random variable takes value 3 and 6. And these two information are put in the tabular form. So on the left side, we put the values, and the right side you assign the probability. So the whole thing we call it probability mass function or probability distribution function. So there is a standard notation that the random variable x takes value small x. Actually, this x is basically x of s, but usually we drop that. Okay, so x takes value small x, and we denote it by pxx. If the random variable was y, then we can denote it by y. The variable inside this bracket, okay, is a dummy variable. Okay, you can put px of t, x takes value t. So it depends upon what value you assign. The subscript, the down subscript or lower subscript denotes the random variable which you are discussing. Say I can write x takes value t. So this will be probability x t, means x takes value t. T you can take 0, 1, 2, 3, whatever you want. Okay. So as you can see, the sum of all these probabilities on the right on this side of the table, that right hand side is 1. So usually sum over all possible values of x each 1. So we call this probability mass function, and it is denoted, as I told you, that pxx, and it has a property that all these values are non-negative, and sum will be between 0 to, sum will be 1, because as you can see here on the right hand side. So now, so this is till this we did it. Now the random variable we can classify as a discrete random variable, continuous random variable. Now discrete random variable means if the values takes are countable. Okay, say for example, when you are tossed the coin 3 times, the number of heads you can count 0, 1, 2, 3. So, and these 0, 1, 2, 3 are basically the values in the range space. So if the range of the mapping contains either finite or countably infinite number of values, then this random variable is called discrete random variable. And if the range includes an interval of real numbers, bounded or unbounded, the random variable is called continuous random variable. So in the previous example, the tossing of the 3 coins, the random variables can be, as I told you, that number of heads can be counted. So it is 0, 1, 2, 3. Now it is a finite. If I am interested in an experiment where I keep tossing a coin till I get the head. Okay. toss a coin till I get a head, and here my interest is the number of trials you need to make, or you need to throw, or you need to conduct till you get a head. Okay, please keep tossing a coin and stop as soon as you get a head. So how many trials you need to perform? So this you cannot tell well in advance. It could be the very first trial. You can conduct 2 trials in which the first trial resulted in a tail, second one gave you the head, then it will be 2, and therefore the range will be 1 to 3. Now, so these are the examples for the discrete random variable, and in fact we will be discussing some discrete distribution where you will learn more things about all these things. Now, live continuous random variable, there are several examples where you can represent the random variable in form of interval. Say for example, life of a bulb. Now, say suppose you buy a bulb, okay, and put it in your room. What is the life? Can you tell in advance? You cannot tell in advance that it will last for 2 hours or 3 hours. Sometimes it happens that you buy a bulb, put in your bulb holder, immediately it gets out of order, means fuse. It doesn't work. So its lifetime is 0. But sometimes you keep the bulb, okay, and years it keep working. So the life of the bulb could be any value from 0 to infinity. Okay. So similarly, say height of the students. So height of the students could be anything between say students are height of a male or female individual could be anything between say 1 feet to 9 feet. In this interval, it will cover almost all the heights which we can think of. So there are many applications where the random variable which we deal is continuous in nature, and many examples where we can count it, count the values of the random variable. A simple example to understand is, I will be using this. You make a queue, okay. For most of the services, you make a queue. You make a queue at a barber shop. You make a queue for taking food in a hostel during the breakfast time, or when you go to the post office or the bank, you have to stand in the queue. So what is special about this? So basically, if you see, there are 3 things. One is that customers who arrive, okay, and they join in the queue, and there is a server who provides this service, and after the service you leave. Okay, so what is specific about this? Okay, the specifically, if you see, there are 3 things. One is the customer arrival. Now this customer arrival is not that for every fixed interval customers are arriving. Okay, somebody arrives, then after say 2 minutes somebody will arrive, or immediately next person will arrive, or it will be a gap of 30 minutes, 15 minutes, whatever it may be there, it is of a random nature. Okay, no fixed timing you can assign that the customer will arrive with a specific interval. So this inter-arrival time, okay, inter-arrival time between the 2 customers. Okay, so inter-arrival time between the 2 customers, say this and this. So this length is continuous. Okay, so we define this as a continuous random. Similarly, the service time. When a customer goes to the server, he has to be served. So now you must have observed, say when you go buy a ticket at a railway reservation counter, what do you observe? Sometimes the customer goes, he gives the slip, and the person who is sitting on the terminal, he gives you the ticket. Maybe your job is done in half a minute. Okay, but you must have seen that some person stands there with the server. He will ask, I have to go from here to Delhi, which train, which type of seat is available. He will keep asking several things. So this time could not be the same whatever the time he has taken to serve the previous customer. So there will be a fixed duration. There will be duration of time, and it will not be a fixed duration. It will be basically a random variable. Random variable means length of the time is not fixed. It could be any value between, say, 0 to infinity. So here the customer service is specified by the time taken to serve a customer. Then we have a number of servers. Many places you can see that there are many servers. They are arranged in the parallel, and there is a common queue, and all the servers provide the same type of services. So as and when any server becomes free, you are called there and you get the service and leave. Okay. Then waiting space could be finite and it could be infinite. Waiting space means, say for example, a cinema hall. If you go to watch a movie and if you have to buy a ticket, you have to stand in the queue. Now, so sometimes the movie becomes so popular that the queue gets longer and longer. So it will stretch up to the road and the next road, and sometimes you must have seen the U-shape of queues are made in the temples. You must have observed. So there is an infinite waiting space. Means whosoever comes, you can join the queue. But there are the places where the waiting space is finite. Means after a certain number of customers, the other customers are turned away. Okay, say for example, in front of the doctor's chamber. So doctor is there outside. Maybe he may be keeping a room for at the most 10 customers. So beyond 10, if somebody arrives, he will be turned away. Then there is a service discipline. Service discipline means the order in which you serve the customer. So usually the first come first serve is the most popular scheme. That it is also known as the first in first out. So first come first serve is most popular. There is another one, last come first serve. There is a priority discipline. Priority means if some VIP comes, the server abandoned the service of the customer who is undergoing service. He serves the VIP and then comes back to the original customer. So there are several schemes. Now in these, what we are interested basically in queuing. When you stand in a queue, what comes to your mind? Or before you go for a service, what comes to your mind? You would like to generally know the length of the queue, or how many people will be there in the queue, or what is my waiting time in the queue. Okay, so all such type of information we need to know from both customer point of view as well as management point of view. Okay, the management means who manages the services. Okay, so there is a area which is known as the queuing theory. So under this subject, we study the different type of queues, the different types of the models are formulated, and the meaningful informations are drawn depending upon the arrival pattern and the service pattern. So we are not going to discuss this in the detail. The basic idea of telling you is that at many times I will be taking an example of this queuing phenomena to explain you that the number, say for example, number of customers will be a discrete random variable. At any time, if you observe the queue, you will be finding either nobody is there, or 1% or 2% or 3%. You cannot say 1.5. Okay, so number of persons in the queue is a discrete random variable. And the second thing is that if you consider the amount of time you have to wait in the queue. Okay, so amount of time you cannot say it is 1 minute, 2 minutes, 3 minutes. It could be any value between 0 to infinity. Okay, so it may so happen that you arrive, you find the server is completely free, means nobody is there in the queue, you are served immediately. So in that case, your waiting time in the queue is 0. Or you may have to wait 1.5 minutes, 2 minutes, 2.5 minutes. So, or you have to wait at least 3 minutes. So all these quantities are needed. And you can see in the same example, we can define the discrete random variable as well as continuous random variable. If our interest is about the number of customers, then it becomes a discrete random variable. If our interest is about the waiting time of the customer, it becomes a continuous random variable. So when we will discuss the exponential distribution and gamma distribution, there I will explain you a little bit more. So it's just to give you some idea, so that here I have written that NT, if you define, it is the number of customers in the queue. So it takes value 0, 1, 2, 3. And amount of time one has to wait in the queue is a continuous random variable. So you have to understand between the discrete and continuous random variable. There is one more definition which is used to classify the discrete and continuous random variable, is by means of the distribution function, which we'll discuss at a later stage. So right now, what I am going to discuss is some of the standard distribution. Okay, what do we mean by the sum of the standard discrete distribution? Means these distributions arise in our real life situations. Okay, so first thing that let us consider, or let us define trial. So we consider a trial. Okay, trial is basically the experiment. It is sometimes we call sub-experiment. So trial is the word. Toss a coin 1 time, it is a single trial. Toss a coin 2 times, it is an experiment consisting of tossing of a coin 2 times. Okay. So now we are considering a specific type of trial. What is specific about this trial is that it has only 2 possible outcomes. Okay. 2 possible outcomes. Means, say for example, when you toss a coin, it has 2 possible outcomes, head and tail. If you appear in an examination, you can get success or you can fail. Item can be classified defective and non-defective. Okay, so we are restricting ourselves with that type of trial which has only 2 possible outcomes. And usually it is represented by success S and failure F. So, okay. Success could be getting a defective item. Failure could be getting a non-defective item. Success in hitting a bird with some pistol. So success means whatever way you want, you can define. Okay. So this particular trial, which has only 2 possible outcomes, is known as the Bernoulli trial. Okay. So we are restricting ourselves with a trial which has only 2 possible outcomes, and more specifically we denote it by success and failure. So the sample space we can write as omega, because this S we are using in the success, F for failure. So instead of sample space notation, which we used capital S, we are in place of this, we are not, we are using, in place of this, we are using the capital omega. Okay. So in a single trial, means we are considering a Bernoulli trial. Okay. So Bernoulli trial is a single trial which has two possible outcomes, which we can write S and M. Here our interest is about a random variable which indicates the number of success. So certainly in a single trial, you will get one success. Okay. So if one success or zero failure. So if I define my random variable X as a number of success, so number of success will be 1 if S comes and 0 if F comes. So our random variable can be represented by X equal to 1 or 0, because it takes two values only. If success, it is 1, 0. So this sample space, okay, are these sample outcomes we have converted in terms of the random variable, where X indicates the number of success. Now, if we denote the probability of success by P, which is standard, then okay, and probability of failure by Q. Okay. So occurrence of success, the probability is P, probability of occurrence of failure, probability is Q, and Q plus P plus Q should be 1. So this probability distribution we can write in this form, as I indicated earlier, that we can put it in a tabular form. On the left side, you have the values taken by the random variable, which is 1 and 0, and here corresponding probabilities. So probability X equal to 1 means probability of occurrence of a success. So probability is P, and probability X takes value 0 means failure. So this probability is Q, P plus Q is 1. Okay. So if I want to write this in form of a mathematical expression, okay. So in mathematical expression, I can write, as I indicated, that Pxx, which is the probability of random variable taking value small x. Okay. So first thing is that we write the range. In any experiment, once you define the random variable, you can always write the range. Now, once the range is specified, we need to develop a mathematical formula. So in this case, it is very simple. It is P to the power x, Q to the power 1 minus x, because if you substitute x equal to 1, you get P. If you substitute x equal to 0, you get Q. Okay. So this particular distribution is known as the Bernoulli distribution. Okay. So we started with a Bernoulli trial, which has two possible outcomes, success and failure, which is a standard notation, and probability of success is P, probability of failure is Q. And in this case, if I am interested in probability of number of successes, then it can be represented by P to the power x, Q to the power 1 minus x, x varies from 0 and 1. So this is the simplest distribution, Bernoulli distribution. Is it clear till now?
Yes, sir.
Yes, sir.
Yes.
Okay. So now we move to the next topic. So we are considering an experiment. As I told you, the experiment consists of several number of trials. So what is my experiment? Experiment is repeating the Bernoulli trial for a fixed number of time, say n. Okay. Say you could fix n as 150. So the trial, which is a Bernoulli type. Bernoulli trial means it has only two possible outcomes, success and failure. That we have specified. We cannot consider the case. We are not considering the case which has three possible outcomes or four possible outcomes. Okay, we are considering the Bernoulli trial. So first thing is that we have restricted ourselves on the Bernoulli trials, and it is repeated for a fixed number of times. Means this you have to fix well in advance. I am saying you toss a coin 100 times. So this 100 is your n, which you have fixed. Okay. Now we make certain assumptions. Assumptions means that your experiment consists of tossing up a coin or repeating a Bernoulli trial. These trials are independent. Okay. Independent means the outcome of one trial should not affect the outcome of the next trial. Okay. Probability of trials, probability of success remains constant throughout the experiment, which is P. Means your experiment, which consists of repeating a particular trial, say 100 times, and each time the probability of success remains constant. It is not like that in the beginning it is say 0.5. After some times you keep tossing the coin, it becomes 0.7, then it becomes 0.8. It is not the situation. We are considering the situation where the probability of success remains constant throughout the experiment. Okay. Now, what is our interest in this experiment? Say, in this experiment, what is your interest? Say, suppose you toss a coin 100 times. Okay. N is 100. Now, what is my interest? My interest is how many times I will get the head. What is the probability I will get 5 heads, 10 heads, 100 heads, no head, 15 heads. Okay. So, in this case, I will define my random variable. What is my random variable? X is the number of successes in n trials. Okay. X is the number of successes in n trials. N we have fixed well in advance. Okay. So if I perform my experiment, which consists of repeating the Bernoulli trial n times, my interest is about the number of success. Okay. So I am interested in finding what is the probability of getting 0 success, 1 success. So first thing is that on this left side we write this one, probability X. This we need to find out. Okay. But as I told you, range you can write always well in advance. Say what will be the range here. Okay. This box we have to fill up. Okay. So our objective is what? To find what is the probability of getting X number of successes, small x number of successes. Now how many successes you will have if you toss it 100 times? It could be 0, 1 to 100. So in this particular case, when we are repeating the Bernoulli trial n times, at the most you can get n success, and the minimum number of success could be 0. So it takes value 0, 1 to n. Okay. So this I can write as soon as I define my random variable. So as I told you, our objective is to fill up this box. Though I have written the expression inside, but generally in the class we write this afterwards. So how do we get this expression? So now if you look at a simple example, n equal to 3, and when you repeat the Bernoulli trial 3 times, okay, and you are interested in getting 2 successes. Okay, So when you repeat the Bernoulli trials 3 times with the objective of 2 successes, so what are the possibilities? The one possibility is that SSF. The second possibility is FSS. Okay, failure, then success, then success. Or you got the success, failure, success. Remember that this you are doing for x equal to 2. Similarly, you can do it for x equal to 0, you can do it for x equal to 1. So these are the 3 possible cases which will result 2 successes in 3 trials. Now, in the beginning, we have made the assumption that probability of success is P and trials are independent. So in this case, the corresponding probability will be PPQ. In this case, QPP. In this case, PQP. So basically, if you simplify this, you get P square Q, P square Q, P square Q, and there are 3 total. Any one of this will give you 2 successes. So we have to sum it. So basically 3p square q. Okay. So 3p square q is the required probability. Or we can write this as a 3c2 p square q. Means out of the 3 trial getting 2 successes. So in general, how do we derive this expression? Say suppose you consider one particular sequence. Okay. One particular sequence which will be of success, failure, and fail. So there will be n trials. Okay, you have performed n trials. Say first trial gave you success, second trial you gave you success, third failure, like that. Now, so if we are interested in x successes, it means you will be getting n minus x failure. So probability will be p to the power x, q to the power n minus x. And like this, there will be NCX. Okay. So NCX, just like here we have sum 3C2. So here there will be, means here you have summed all this, then you got 3p square q, which is basically if you use the permutation combination, getting 2 successes out of 3. So 3C2. So NCX. So if we combine all these things together, we get a formula which is NCX p to the power x q to the power n minus x, and range we have already. So this particular distribution is known as binomial distribution. Now, as you can see, what is the condition for probability mass function? It should be greater or equal to 0 and summation should be 1 for all possible values. So here the summation I have done it, x equal to 0 to n, ncx p to the power x q to the power minus x. And this sum is nothing but q plus p to the power n, which is q plus p is 1, so it is 1. So it is a valid probability distribution. So this distribution is known as the binomial distribution, and it has 2 parameters basically. So in statistics we use several symbols instead of writing binomial distributions. So what we do, we specify them by B and P. So B means binomial, and inside the brackets are the parameters. So n is one parameter, p is another parameter. What is n? Is the number of trials which you have to fix well in advance. Means you have to tell how many times you have to repeat the experiment. And p is the probability of success. That also you have to tell. So here in short, what we write, x follows this symbol we use, x follows. Okay, so you can something like this, it is there. So you have, so x, this symbol we use, this is the random variable which we know in this case is the number of successes. It follows the binomial distribution with parameter n and p, where n is the number of trials P is the probability of success. If we take n equal to 1, means in a single trial, what will happen? We can write x equal to, x follows B1P. Now it is a Bernoulli. Now another thing you can observe that these probability of getting 0 success, 1 success, 2 success, n success is nothing but the individual probabilities are basically, if you expand this q plus p to the power n, p you know, n you know, q you know. Okay, so this first, if you expand this, so q to the power n, nc1, q to the n power n minus 1 into p. Similarly, you can expand this we using the binomial theorem. So the first term gives you probability of x equal to 0. What is x equal to 0? Probability of getting no success, 0 success. Means all the outcomes resulted into the failure. So n times you have repeated the experiment, all times you have got the failure, so q to the power n. Similarly, the last term will be all the time you have got the success, so it is p to the power n. So second term will give you the probability of x equal to 1. Third term will give you probability of x equal to 2. Okay, so like that, sometimes what the student do is that if p and q is given, say suppose n is 10 and p is 1 by 3. 1 by 3, q will be 2 by 3. So what you do if you have to expand this? So here you can write 2 by 3 plus 1 by 3 and expand using the binomial theorem, and then corresponding probabilities you can extract. So this is one way, or you can just directly calculate if I need what is the probability of getting 5 successes if n and p are specified. You can directly substitute it. You can get it. So basically, what you have to understand in this binomial distribution, usually in the Viva or many places, we ask for the students are asked to explain the binomial distribution. So in those situations, instead of directly telling that NCXP to the power QX, because most of the times we have seen the student remember the formula NCXP to the power X, Q to the power N minus X. They say this is binomial distribution. But what is the meaning? Okay, what is probability X equal to X? That they are not able to tell. Okay, so you have to tell, you have to understand what is X. X is the number of success in a fixed number of n trials. This n is fixed, and each trial is a Bernoulli trial. Means it has only 2 possible outcomes, success and failures. Trials are independent, and probability of success remains constant. Under these assumptions, the distribution of the number of successes follows the binomial distribution with parameter n and p. Is it clear?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So we have discussed Bernoulli binomial. Bernoulli is a special case of the binomial. Okay. Now, I will just change the definition of now my random variable. Okay. Experiment is same. Means we are still considering the Bernoulli trial. Now, what I am telling you, toss a coin till you get a head. Okay. Or keep performing your trial till you get a success. Okay. So here I have just changed the definition of the random variable. Now X denotes the number of trials until the first success. As soon as you get the first success, you will stop the experiment. Okay. So what is our interest here? our interest is knowing the distribution of the number of trials. Means what is the probability that you need 5 trials, 3 trials, 4 trials? Okay. So experiment is same is we are still considering the Bernoulli trials. Trials are independent. Probability of success is P, but X I have changed here. Okay, which is the number of trials until the first success. So as I told you, we need to find the probability X equal to X. This we can write. We will write first. Okay. Now range you can always tell. What will be the range? When you have to perform the trials until you get the first, until you get a success. So it may happen that in the very first trial you can get the success. Second trial, first failure, then success. Then first failure, second failure, then success. So number of trials will be 3. So like that, I can always specify this part. Okay, X equal to 1 to 3. X we have defined. Okay. The values taken by the random variable, that I can write value. Then next question that we have to fill up this box, which I have written q to the power x minus 1 to p. So this I have written after considering the various, means basically this is the formula you need to find out. Okay. So before you need to find out the formula, what do you need? Means you need the distribution of the number of trials, which we have defined by X. So what will be the distribution of number of trials? The values taken by this random variable is 1, 2, 3. So we need to find out some expression where I can substitute X equal to 1, X equal to 2, and I can get the result. So now look at this. How do we get this? So you may get success in the very first trial. Okay. You may get success in the second trial, which first failure, second time you got the success. You have 2 failures, then success, and like that. So in general, if you look at that, here in the very first trial we have got the success. So number of trial is 1. Here the number of trial is 2. Okay. Here the number of trial is 3. Okay. So in general, if we have to perform X number of trial, okay, means you need to perform X number of trial until you get a success. So it means the last trial is always a success, as you can see here also. As soon as you get the success, you stop the experiment. So if it is the X number of trial, the last trial, which is Xth trial, and it is a success. Okay. So since the trials are independent, probability of success is P, probability of failure is Q. So this whole thing will become Q to the power X minus 1. As you can see, this total number of trials are X. So X minus 1 failure, 1 success. So Q to the power X minus 1. So here in this case, Q is square P. So number of trial is 3. So Q is square P. QQP. So in general, you get, if you are interested in X number of trials until the first success, then it will be X minus 1 failure, and the last trial will result in the success. So Q to the power X minus 1. So this is the formula. We have to check whether it's a valid distribution or not. So basically, it is a non-negative quantity. As you can see, both P and Q are positive. Okay. Let us see this sum. So we have to sum all the possible values of X here. Okay. So if you sum this, it is a geometric series. Okay. So it will be P over 1 minus Q. 1 minus Q is P. So it is 1. Okay. Now This distribution is known as the geometric distribution. Okay. So as I told you that X and this symbol, which we call it follows. Okay, X follows the geometric distribution. So in short, we write X geo. Geo means geometric with parameter P. Here we are not fixing the number of trials. Okay, we are saying that we need to perform as many as trial until we get the success. So there is only one parameter, which is probability of success of P. Is it clear? So this particular distribution is known as the geometric distribution. So geometric distribution is the distribution of number of trials until the first success. Simple. Okay. Is it fine?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now I will change the definition of the random variable. I am changing the definition Y. New random variable I am defining with the same experiment. Okay. Now the number of failures until the first success. You have to count the number of failures instead of number of trials. I may be interested in knowing the distribution of the number of failures until the first success. Okay, how many times one failed to get a success. Okay. So as I told you, first I will write this one. And the range will be what? So I have written here 0, 1, 2. But you can see that number of failures until the first success. Means number of failures could be start with 0. Because if you have got in very first trial, say if you look at this here, the number of failure is 0 here. Okay. In this case, number of failure is 1. Total number of trial is 2, but you got 1 failure. In this case, you got 2 failures. Okay. So here the range will be from 0, 1 to so on. Now, as you can see, the distribution will be q to the power y into p. Okay. You can obtain like this from the previous one. What is y? Y is x minus 1. Number of failure is equal to the number of trials minus 1. That's what if you look in this example, total number of trials you perform 2, 2 minus 1, 3 minus 1, 2 trials. Okay. So probability of y equal to y is equal to x minus 1 equal to y. Okay. If I use this formula, this connection between x and y, and since we know the distribution of x, okay. So x minus 1 equal to y, it means probability x equal to 1 plus y. Since we know the distribution of x, I can write q to the power 1 plus y minus 1 into p. So which is q y to the power p. So this one, sometimes we call it modified geometric distribution. Here also, if you sum for all possible values, you will get the sum. So in one case, you have the distribution of number of trials until the first success. In the second case, you have a distribution of the number of failures until the first success. So these two are different. So why I have started with this way. From the beginning, we have a random variable we have defined, and you consider the experiment, keep changing the definition, keep changing the definition of the random variable, your formulas will keep changing. Okay. So let us start. In the next class, we will discuss this property, memoryless property of this distribution. go through. If you have any doubt, then we can discuss tomorrow. So shall we stop it?
Thank you, sir.
Uh,
Okay,
Thank you,
sir.
sir.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.